back to the second session, right. So, in the previous session we discussed about the basic introduction to the state variable, and we had seen the basic definition of state variable, why we use state variable, what is the basic importance we had seen in the previous session. So, in today's session we will discuss about the state space representation. We will see the example of state space model, right, and then we will see the relationship between the state equation and higher order differential equations. Okay. So, this slide that we had seen in the last session, right. So, where our state equation given by this equation, this is known as state equation, and the second equation is known as output equation, and you can see the order of our A matrix, this is known as state matrix, which will tell us how the state variable connected inside system, how they are related to each other. It is governed by the A matrix or state matrix. It is order of n cross n, where n is the number of state variable. Then x is the state vectors, how many state vectors are present. Then B is the, you can say, input matrix, which will tells you how the state variable affected by my input quantities is given by the B matrix. Order is n cross m, where m is number of input present in the system. If I am using a single input, that is SI system, then order is n cross 1. If I am using multiple input, suppose 2 input, then order is 2 cross 1. So, depending on, it is n cross 2. Okay. So, depending on the number of my input, m value will change, and U is the input matrix. Okay. So, input, this is the scalar vector, scalar quantity, right. This is the U is scalar quantity given by m cross 1, where m is the number of input. The same way y equal to C p cross n, where p will tell you number of output, n is the number of state variable, x state vector, D is the feed forward matrix. So, I told you in the previous session that it is used to bypass our input from the system. Okay. So, this is the modeling of the state, you can say state diagram of this equation. So, here you can see that y equal to C, we will start from the state equation, x dot equal to A x plus B u. So, here if I am having x dot and I want to obtain the x, so what I will do, I will integrate x dot, what I want to say, if I am having dx over dt and I have to obtain x. So, what I will do, I will add here integrator in between them. So, this is my x dot t and I want to obtain x t. So, I have to use this integrator. So, to represent this equation in state equation, I am using here a adder. So, I will use here a summer which will perform this operation. So, it is combination of two, one is a state matrix, second is the input matrix. So, input I am setting here u t, it is multiplied by b. So, b is here. So, b times u is my one input of this adder, second input is a times of x. So, x t is obtained here, x t is with me. If I use a in the feedback and provide input to the summer, then I will get here x dot equal to b u. From here I will get a times of x plus a times of x will obtained here. So, in this way I can model my state equation from here. The remaining thing, that is y equal to C x plus d u. So, C x is available with me, I want to obtain C x, I will add here a gain block of C, here I will get C x plus means one adder d u, d times of u. So, here my u is coming directly and it is coming here. So, this is my output equation. So, this is a state diagram of this equation. Okay. Now, state space representation we will see. So, here x 1 dot, you can say the derivative of state variable may be function of x state vector and it may be function of u, that is number of input. So, whatever input I am applying, it is going to affect my state variable x 1 and then it will affect the x 1 dot. So, in short I can say x dot is function of x and u. Okay. We will talk about t later. In the same way, if we see the output equation, the y 1 is given by g times of x 1, it means it is depending on state vector x and depending on my input variable. So, my output equation again the function of x and the input u. So, I can say my y t is function of x and u. If I am dealing with the static type of system, in that case I will make t equal to 0. Okay. So, I will make what? T equal to 0. Whenever I am dealing with the time varying system, then I will make here t as a function of x dot t. The same way here I will make this t as a function of y t. It means both state and output varying with time for a time varying system. Okay. Now, we will see this example of a mass spring damper system. This system we discussed in unit 1, and if we write the equation of the system, which is the differential equation, we can say mathematical modeling of this equation, and now we want to obtain state space model from this differential equation. Okay. So, what we will do, step 1, determine the number of state variable. So, I told you the order of this differential equation will give us the number of state variable. Okay. So, first I will assume here this x equal to x 1, dx over dt would be, you can say x 1 dot, and I can say it is the new state variable x 2, d 2 x over dt square can be written as x 2 dot, normal differential equation. Okay. So, now from this equation I will determine value of d 2 x over dt square. It is equal to f by m. I will take f by m here, I will multiply by m divide by m everywhere, and I will obtain this equation. Okay. By adjusting the LHS and RHS quantity, I will obtain this equation. Okay. And from this equation I would like to write the state matrix. Okay. So, one matrix, you can say one derivative equation is in terms of x 1 dot, right, this is the equation number 1, second is x 2 dot, this will be the equation number 2, and I have to obtain the state space model from these two equation. Okay. So, you can see this derivative equation basically give us the state space model. So, here I am getting x 1 dot equal to x 2 dot 0 1 minus k by m minus b by m, order is here 2 by 2 because we are using here two state variable. So, from equation 1 x 1 dot equal to x 2 plus 0 times of x 1 because x 1 is absent. So, I can make the first row of this matrix as 0 1. Okay. Here x 1 x 2 is here in this matrix as a column. Second row, the coefficient of x 1, you can say it would be minus k over m, and coefficient of x 2 minus b over m. This will be the second row of the matrix minus k over m b over m. Now, this is my input. Okay. So, what input I am providing? Force f by m, this is my input quantity. Okay. I am applying force as the input, then I am getting changes in the output of the system. So, force is the input, that is f by m. It is available in equation number 2, it is absent in equation number 1. So, I can say my input is not present, that is 0. So, here I can say 0 in row 1, f by m in row 2, this is my input of m cross 1. Here my input is 1. So, that is why it is 1 cross 1 order, and this here it is n cross m, 2 state variable, number of input is 1. So, order is here 2 cross 1. Now, this is my y, here output is single, that is one force is coming at the output. So, its output p value is equal to 1, n is 2. Okay. So, for this I need to see my output matrix y. Okay. So, I can model here, I am getting the output in terms of this, you can say x 1 and x 2. So, this force element is applied here. Okay. So, here you can say around the x 1 mass m 1 that you can say. So, here this output equation is written as 1 0 multiplied by x 1 or x 2, it means y basically is given by in terms of x 1. Okay. So, this is the modeling. So, this is the modeling of this mass spring system, right. So, in the same way, if we see second question, that depending on the above steps determine the state variable matrix of the following transfer function. So, this transfer function is available to us and we need to obtain the state space model. Okay. So, what we will do? We have to arrange it in terms of differential equation. So, basically the process to obtain the state space model from a given transfer function is known as transfer function decomposition. Okay. So, we need to apply the decomposition method to obtain the state space model. It means I need to convert it into differential equation, then I will obtain the these basic step to obtain the output. Okay. So, here this is the state diagram for this. So, here what is happening, I am getting here dy by dt and y is here, it is here d2 y over dt square. It means, if I want to represent in terms of state diagram, or you can say in terms of SFG. Okay. So, what I will do, I need to observe this thing, whenever I have to obtain y from dy by dt, it means I need to do here integration. In the same way, whenever I have to obtain dy by dt from d2 y by dt square, I need to use here integrator. It means, the number of integrator in the system depends on the order of this equation. So, here order is 2. So, I have to use here 2 integrator. Okay. So, basically if I write in terms of the state variable, this is x 2 dot plus 2, you can say it is x 1 dot plus 3 y, that is 3 times of x 1 equal to 4 u, if I assume y equal to x 1 as a state variable. Okay. So, now you can see here this highest order, this x 2 dot will be the first. Okay. So, plus symbol is coming here, second plus is here, it means I have to use here 2 adder. Okay. Then input is coming from this side, it means 4 times of u is coming here. Okay. So, at this adder you can say this is that second adder regarding the x 2 dot. So, it is receiving what 2 times of x 1 dot. So, whenever x 2 dot is here, integrator x 2 is coming. So, now from here 2 times of this x 2, okay, you can say x 1 dot is basically equal to x 2. If you see the previous definition, x 1 dot is equal to x 2. So, I can say it is plus of 2 x 2 instead of x 1 dot, only to simplify, right. So, here dy by dt is, you can say x 1 dot is here, whenever I differentiate this x 2 dot, I will get here x 1 dot, and 2 of x 1 dot is here, it will available to this adder. So, this function is completed. Now, second adder is here, it is 3 times of x 1. It means, from this x 1 dot I have to obtain x 1, it means I need an integrator, and this x 1 will come with the coefficient of 3 and add to the system using this adder. Okay. And 4 u is coming through it. Okay. So, this is the mathematical modeling for this, for the state representation of this equation. So, if I write this model, so I will assuming y equal to x 1, dy by dt as x 1 dot equal to x 2, d2 by dt square as x 2 dot, d2 x over dt square as this one equation, right, 4 u minus 3 x 1 minus 2 x 2. So, that is why I am assuming here as a plus 4 u t and remaining 2 coefficient as minus in the summation. Okay. So, this is the step of modeling. So, first I have to assume state variable like this, my first variable y equal to x 1, differentiated dy by dt both side x 1 dot, I will assume as x 2. Now, again differentiate d2 by dt square, this will become x 2 dot. This is a basic step. Now, the highest order term I have to keep in LHS and remaining term I have to keep in RHS, and then I have to make this modeling. Now, make this equation state space modeling. So, 2 state variable x 1 dot x 2 dot would be here. In the first equation, you can say this is my first equation, x 1 is absent. So, here it is 0 1, then you can see in the second case minus 3 is here, minus 2 is here, coefficient of x 2, plus input you can say it is only 4 available in equation number 2, absent in equation number 1. So, I can say 0 and 4. Okay. And if I talk about the y, okay, so y equal to x 1, this is my equation number 1, this is my output equation. So, y is only equal to x 1. So, 1 coefficient is here and x 2 is absent. So, I can write here plus 0 times of x 2. So, 0 is here, this is my output equation. So, this is the way that I can write the state model of a mass spring system, right. Now, I will see the basic relationship between the state equation and higher order differential equation. This will give us the generalized picture of state space model. Okay. So, this is my nth order differential equation d n y over d t n plus a n d n minus 1 y d t n minus 1 plus dot dot a n y equal to u t. Now, I will start from assuming y equal to x 1. This will gives me the output equation. Now, differentiate dy by dt equal to x 1 dot will gives you x 2. Now, further differentiate d 2 by dt square gives you x 2 dot, assume it at x 3. So, where you have to stop, you have to see the highest order. If highest order is 2, you have to stop here. If highest order is 3, you have to stop here. In the same way, whenever highest order is n, it means you have to stop at x dot n, right. So, here I need to stop at x dot n, right. And now, I will equate this term equal to u t minus all this term in the RHS, and this equation will obtained, right. Now, I will replace all this y dy by dt by state variable. I assume y equal to x 1, I will write here x 1. I assume dy dt equal to x 2, I will replace it x 2. So, in this way nth order equation is here, and if I represent them in terms of matrix. So, I will get here, you can say the state variable matrix will be given by this derivative variables, that is x 1 dot, x 2 dot equation, x 3 dot equation will gives you the state space model. We do not have to include the first equation because it will give us the output state. So, here x 1, x 2, x 3, x n dot, sorry, x is basically the state vector is here, a is the input, sorry, state matrix. So, if I see the matrix, you can say x dot equation. So, x dot equation or matrix would be given as x 1 dot, x 2 dot till x n dot, okay. And where a matrix you can say 0 of 1, okay, because a matrix 0 element is x 1, x 1 coefficient is 0. If you see the coefficient of x 3 0, x 4 0 till nth order, only coefficient of x 2 is present. So, that is why second element is 1. In the same way, in the second row third element would be 1, in the same way third row fourth element would be 1, and this matrix will go on, and in the last element or last row I will get all this coefficient. Okay. So, you can say a 1 is here, a n minus 1, right, till a n. So, a 1 is here, a n minus 1 till a n, it is coming in this way. Okay. This is the B matrix. So, only single input. So, at the end I am making 1. Okay. For output matrix y equal to x 1 only, all the coefficients are 0. So, it is 1 till n 0 p cross n, and only x 1 will present, remaining x 2 to x n would be 0 if you do this multiplication. So, this is my output matrix. This is known as vector matrix representation of state diagram. Okay. So, now state diagram we had seen, the significance is that it will gives you the close relationship among the state equation, and it will helps you in computer simulation. Okay. So, it can be constructed directly from system differential equation, and it allows you to determination of system state variable and state equation. To obtain the state diagram state space model from a differential equation, this is known as decomposition of transfer function. Okay. So, how to do this? This is the basic step, right. So, here this differential equation is given to me nth order. So, what I will do? I will keep my highest order in the LHS and all the variable in the RHS. Okay. Then I have to take Laplace transform in both the side. This will give me Laplace transform. Okay. Now, I have to arrange this dot matrix. Okay. You can say this dot dot, I have to create the number of nodes. First node corresponding to the input, last node corresponding to the output. input is my here r t. So, I am assuming r as my input node, output is here y. So, I am assuming y as a output node, and same thing whenever I have to go from, or whenever I have to obtain y from dy by dt, it means I need to do integration. If I talk in Laplace domain, if I am getting here s y and I have to obtain this y, I will do the integration, that is 1 by s, and I will get here y. So, in this domain for integration, what I will do? I will use here 1 by s, right. So, here I have to replace this, you can say r t r y as a output, y is here. Okay. So, now I have to look for the highest order term is here s raised to power n y. If I take a Laplace, this is my output. So, I am using this node as my highest order y, you can say highest order node is here s raised to power n y. Now, if I have to obtain s raised to power n minus 1, what I will do? I will add here a integrator 1 over s. If I have to go for s to the power n minus 2, what I will do? I will add here a integrator. It means in each and every step I will keep going on adding the integrator in this way. Again, number of integrator is equal to highest order, that is n. So, n number of integrator I have to use. Now, here this equation is equal to plus of r s. So, r s is coming to the input. So, I am saying r is coming to the input to this node, okay, and it is receiving minus of a n times of s n minus 1. So, this is my s n minus 1 y. If I take minus of a n coefficient here, you can say gain, then I will get this equation, right, because this SFG part we have done in unit 1, you can refer those lectures. Okay. Now, I need to obtain s n minus 2 coefficient, which that is minus a n minus 1 would be present here. Suppose this equation would be, after that I am writing here minus of a n minus 1 s raised to power n minus 1. So, this n minus 2. So, this n minus 2 coefficient having minus a n minus 1. So, it will come like this. Similarly, minus a 2, similarly minus a 1, and I will complete them by integrator. This will complete the diagram. Now, how to model the state variable? So, I will start here, this will gives me the x 1, this will gives me the x 2 dot, sorry x 1 dot, this will gives me the x 2 dot, then x 3 dot. What I want to say, I have to make this node where I am getting the highest value. I am assuming this is x n dot, next would be x n minus 1 dot, the last one you can say if it is x 1, this node would be x 1 dot, next node would be x 2 dot, then next node would be x 3 dot. So, this sequence of the state variable I have to apply. Okay. So, this is the overall SFG for this equation. Okay. So, what is the importance of this diagram? That we can obtain output from mid node that will explain the behavior or dynamics of the system in terms of state diagram. So, this will tells you the value of state variables present in the system. Now, this is the second example which will explain that step. I am assuming this equation, I have to obtain SFG from this equation. So, I will keep highest order in LHS, remaining in RHS. I am assuming RT as the input and y as the output at my last stage. Okay. Now, d2 y by dt square, it means I need here an integrator. I will take Laplace of it, s square of y equal to minus 3 s times of y minus 2 y plus r of s or r. Okay. They all are function of s y, that is. Okay. So, if I see here, this is my input. So, s square y is present here, it is receiving plus of r s. So, r s plus is coming to this s square y and minus of 3 s. Now, I obtain, I am having s square, now I have to obtain s. What I will do? Integrator 1 by s. So, I will add here 1 by s to obtain s y. So, which coefficient of s y? minus 3. So, minus 3 coefficient is going to add here. In the same way, when we go for y, it means now s y is with me, I have to obtain y, what I will do? Integrator, right? I have to add integrator in between them. So, I will add s inverse and this will gives me y, okay. And what is the coefficient? Minus 2. So, minus 2 is coming here and this will complete the diagram. My starting node would be x 1, second node would be x 1 dot, this node last one would be my x 2 dot, right. So, this is the complete SFG of this equation, right. Now, we will come for the canonical form, right. So, if I have to represent the state model in terms of SFG, so what I will do? I will take the reference of the previous step. So, whatever step that we had seen in this case, okay. So, this is basically tell us the canonical form representation of state space model, right. So, what is happening in canonical form? We are doing what? We are representing one variable as the output and remaining variable as the derivative of output. This is the representation of canonical form. Okay. It means this type of representation of a state space model is known as canonical form representation, right. It means our one variable is the output, you can say here y equal to x 1, this is my one variable, okay. And remaining variable would be derivative of output, that is dy by dt, d2 by dt square, dq by dt cube, they all are what? Derivative of my output quantity. So, this type of representation is known as canonical form. So, it is having the various type, one is the phase variable canonical form, second is controllable canonical form, both are basically equivalent. Next is observable, diagonal and Jordan canonical form. So, it is the various method that we will use to represent a state space model. Till now, whatever we studied about the modeling of state space model, we had used the canonical form which is equivalent to the controllable canonical form, and that method also known as phase variable canonical form. Okay. So, it is again this group is known as companion form, and this bottom group diagonal and Jordan, they are again equivalent. I will tell you what is the basic difference between them. It is known as model form. Okay. So, that is decomposition of the generalized equation we will see in the next lecture. Okay. So, thank you for today, right.